Welcome to our journey into the fascinating world of insect vectors and diseases. Today, we're going to explore exactly how different insects eat. It might sound like a simple topic, but the microscopic engineering of insect mouthparts is actually one of the most incredible evolutionary stories in all of biology. Let us dive in and discover how form meets function. To start, imagine trying to eat a crunchy apple without teeth. Impossible, right? Insects face this exact problem when eating tough leaves or wood. To solve this, nature developed biting and chewing, or mandibulate mouthparts. These act exactly like heavy-duty scissors. The mandibles are the primary jaws, moving horizontally to cut and crush. They are assisted by the labrum, maxillae, labium, and a tongue-like hypopharynx. This primitive design is crucial because it allows insects like cockroaches and grasshoppers to break down tough organic matter, driving nutrient cycling in our ecosystems. Now that we understand the anatomy of these jaws, let us look at the physics behind their crushing power. We can model the insect mandible as a simple lever system. The formula here shows how muscle force is converted into bite force. FB is the actual bite force on the food. FM is the force from the insect's internal muscles. L in is the in lever length, and L out is the out lever length. Physically, if the insect has a longer in lever, the bite force increases. But if the out lever is longer, the bite force drops, though the jaw can snap shut much faster.
Before we move on, let us see this formula in action with a concrete example. Imagine a cockroach biting a tough leaf. Its internal muscle generates a force of 0.5 newtons. The in-lever distance is 2 millimeters. And the out-lever distance to the tip of the jaw is 4 millimeters. We want to find the actual bite force applied to the leaf. By applying our lever formula, we find that the final bite force is 0.25 newtons. This means the jaw's elongated shape actually halves the raw muscle power, optimizing for a fast, wide bite rather than a slow, crushing one.
So we know the final answer is 0.25 newtons, but let us prove exactly how we get there mathematically. We start by substituting our known values into the lever equation. We plug in 0.5 for the muscle force, 2 for the in lever, and 4 for the out lever. The ratio of the levers, 2/4, simplifies to 0.5. This fraction is the mechanical advantage of the jaw. Finally, multiplying the 0.5 Newton muscle force by the 0.5 mechanical advantage gives us our exact result of 0.25 newtons. The math perfectly reflects the biological design. Let us visualize the math we just proved. Here, you see a schematic of the insect's mandible acting as a horizontal lever. Notice the pivot point, or fulcrum, in the middle. The internal muscle attaches at the back, pulling with force F sub m over the short distance L sub in. This pivots the jaw, causing the sharp tip to exert the bite force F sub b over the longer distance L sub out. This geometric setup is the foundational anatomical design that allows herbivorous insects to thrive. Now that we have mastered biting mouthparts, let us look at a completely different challenge. Imagine drinking a thick milkshake through a microscopic straw. That is what mosquitoes do. They use piercing and sucking mouthparts, highly modified for a liquid diet. The labium forms a protective sheath around sharp, needle-like stylets. These stylets pierce the skin, while the hypopharynx injects saliva containing painkillers and anticoagulants. Then, the labrum acts as a hollow proboscis to vacuum up the blood. This specific adaptation leads us to the most medically important concept in entomology. Why are mosquitoes so dangerous? Because this exact feeding mechanism is how deadly diseases like malaria, dengue, and Zika virus are transmitted. When the insect injects its saliva to stop your blood from clotting, microscopic pathogens hitch a ride directly into your bloodstream. Understanding this anatomy is the first step in developing physical barriers and medical interventions to protect global public health. To understand the immense physical challenge of drinking blood, we model the proboscis using the Hagen-Poiseuille equation for fluid dynamics. Here, Q is the volumetric flow rate of the blood. Delta P is the pressure difference created by the mosquito's muscular pumps. The variable R is the internal radius of the tube, eta is the dynamic viscosity of the blood, and L is the tube's length. Notice that the radius R is raised to the fourth power. This means even a tiny decrease in the tube's width makes it exponentially harder for the mosquito to drink. Let us apply this fluid dynamics formula to a real mosquito. A female mosquito needs a flow rate of 10 to the negative 12 cubic meters per second. Her proboscis is 2 millimeters long with an incredibly tiny radius of 10 to the negative 5 meters. Human blood has a viscosity of 4 times 10 to the negative 3 Pascal seconds. We need to find the pressure her head pump must generate. The final answer is a staggering 2,038 pascals of negative pressure, an incredible feat of biological engineering. How did we arrive at that massive pressure value? Let us prove it by rearranging our formula. We start with the Hagen-Poiseuille equation, which is solved for flow rate, Q. But we need to find the pressure difference, delta P. We isolate delta P by multiplying both sides by 8 times eta times L, and then dividing by pi times r to the fourth power. This rearranged equation clearly shows that required pressure is directly proportional to viscosity and length, but inversely proportional to the fourth power of the radius. Now, we substitute our numerical values into the rearranged equation. The numerator represents the resistive forces of the fluid and the tube's length, which multiplies out to 64 times 10 to the negative 18. The denominator represents the geometric capacity of the tiny proboscis, which becomes 3.14 times 10 to the negative 20. Dividing the numerator by the denominator gives us approximately 2,038 pascals. This proves that the mosquito's tiny head muscles must generate immense suction just to draw a microscopic drop of thick blood. Let us look at a visual representation of this incredible biological syringe. Here, you can see the mosquito's proboscis piercing through the epidermis and dermis layers of human skin directly into a blood vessel. Notice the muscular pump in the insect's head. This is the pump generating those 2,038 pascals of negative pressure, delta P, to overcome the fluid resistance of the viscous blood. This highly evolved mechanism is exactly why mosquitoes are such efficient and dangerous disease vectors. We have seen insects that chew and insects that pierce. But what about insects that just want to drink exposed liquids, like flower nectar? They use sponging, siphoning, or lapping mouthparts. Houseflies use a fleshy, sponge-like labellum to soak up liquids. Butterflies and moths use a long, coiled tube that uncoils using internal fluid pressure to siphon nectar from deep flowers. Honeybees combine traditional mandibles with a hairy, tongue-like labium to lap up sweet liquids. These adaptations maximize intake with minimal effort. These fluid-feeding mouthparts are ecologically vital. Butterflies and bees rely entirely on them to reach nectar, and in doing so, they transfer pollen between flowers. This sustains global agriculture and plant reproduction. However, there is a dark side. Sponging mouthparts in houseflies are medically dangerous. Because the fly regurgitates saliva to dissolve solid food and then sponges it up, it mechanically transmits dangerous pathogens like cholera and typhoid from feces directly to human food. The sponging action of a housefly relies heavily on a physics principle called capillary action. We can model how high the liquid rises into the fly's feeding tubes using this capillary rise formula. Here, h is the height the liquid rises. Gamma is the surface tension of the liquid, and theta is the contact angle. Rho is the fluid density, g is gravity, and r is the tube radius. Physically, the liquid will rise much higher if the tube radius is very small, or if the surface tension is high. Let us see how powerful this capillary action is for a housefly landing on sugary water. The microscopic tubes in its mouthpart have a tiny radius of 5 × 10⁻⁶ meters. The water has a surface tension of 0.07 newtons per meter and a density of 1,050 kilograms per cubic meter. Assuming a contact angle of 0 degrees, we want to find the theoretical height the liquid could rise. The final answer is an astonishing 2.72 meters, showing just how easily the fly can feed. Let us prove how we calculated that massive theoretical height of 2.72 meters. We start by substituting all our given values into the capillary rise equation. The numerator represents the upward pulling force caused by the liquid's surface tension interacting with the tube walls. We plug in 2 times 0.07 times 1. The denominator represents the downward pull of gravity acting on the mass of the liquid inside the tiny tube, which is 1050 times 9.8 times the radius. Now we simplify the math to get our final result. Multiplying the terms in the numerator gives us 0.14. Multiplying all the terms in the denominator together gives us 0.05145. Dividing 0.14 by 0.05145 yields a theoretical rise of 2.72 meters. Obviously, the fly's mouthpart is only a few millimeters long, but this massive theoretical height proves that capillary action provides more than enough upward force to instantly and effortlessly fill the fly's feeding tubes without any muscular pumping. We have covered a lot of ground today. Let us summarize the 3 main takeaways. First, biting and chewing mouthparts use horizontal lever mechanics to crush solid food, forming the base of terrestrial food webs. Second, piercing and sucking mouthparts act as biological syringes, using immense negative pressure to draw blood, making them dangerous disease vectors. Finally, sponging and siphoning mouthparts elegantly use physics like capillary action to consume exposed liquids, driving global pollination. You now understand the incredible biophysics behind insect feeding.